So the lesson that you missed on September 23rd, that day we actually went over exponential functions, which is really just a review of what we learned in grade 11. So if you remember back, exponential functions are basically where you have a base number and it's raised to the power of the x value, and then whatever transformations that there are, but the base one is just a base number to the power of x, and you can see that on the screen right here, and you can see that it's actually exponentially growing and that there is a horizontal asymptote, and those are the two main properties of exponential functions. So like I said, the base function of an exponential function is b to the power of x. And then here I drew an example with the base of 2, but this base can be anything. So adding transformations to an exponential function like the base function can actually make the exponential function more complex. So for example, you could shift the graph or the function up or down, left or right. You could flip it over the horizontal axis or the vertical or the y-axis or the x-axis. You could stretch or compress them both vertically and horizontally. So some of the properties that we actually learned are transformations that we applied last year. I'm going to just refresh our memory with that. So a vertical shift actually also shifts both the graph and also the asymptote. So when you have an exponential function that actually did not shift, the asymptote would be at the x-axis, or when y is equal to 0. But when there is a vertical shift up or down, that asymptote as well as the function shifts. So here's an example, and the way you would know if an equation actually shifts the exponential function is that there is a number that at the end of the whole function that is added or subtracted, and in this case you can see that there's 2 added, which means that the function actually shifted up by 2 units. Or if it's a negative number, the function would actually shift downward. Okay, and then if you want to see if a graph shifts left or right, that would be in the exponent, and we would have to actually find the factored version of that exponent. And inside that factored version, you actually use the opposite direction of that sign. So for example, here we have x minus 3, which is already factored, and you see that it's a minus 3, but we have to use the opposite direction of that sign. So instead of going left, you actually shift by 3 units to the right. Okay, and then a horizontal stretch and compression. We have to use the factored version again, and it's that coefficient that actually determines if it's a stretch or compression. And here we have to take the reciprocal of that factored number to see if it's a stretch or compression. So for example here, the factor was 2, and when you take the reciprocal you get a half, and you can see that the graph is actually compressed by a half. Okay, and then if you have a vertical stretch, that is the coefficient that's at the beginning of the function or attached to the base function. And here you can see that each of the vertical or the whole graph is actually stretched by a factor of 3. Okay, and then there are many properties that we also went over. So domain, range, y-intercept, x-intercepts, we learned those last year, and then the 5 new ones that we learned this year were positive, negative, increasing, decreasing intervals, and end behavior. And when I do the example later on in the video, I actually go through all of these in more detail. But domain is basically restrictions on your x values, and range is your y values. Y-intercept is where your function crosses the y-intercept. X-intercepts are where your function actually crosses the x-intercept. And then positive intervals are basically whenever the function is above the x-axis, and negative is whenever the graph or function is below the x-axis. Increasing interval is whenever the function is increasing, and decreasing intervals is when the function is decreasing. And then end behavior is basically showing like in what direction is y going, like the trend of the graph. So when x is going towards infinity, what direction is y pointing towards? And same with the other way around. When x is pointing towards negative infinity, what way is y actually going? And I'll go into more detail when I do the example. We didn't completely learn the inverse of exponential function, but we did actually graph them. So we saw a graph of an exponential graph, and then we inverted the plots, the points, and we were able to graph it. And yeah, we're gonna do an example of the example that we did in class, which was the board work we did now. This is the work that you missed on September 23rd. This is actually the work, this is the exact problem that we did together as a class in boards and as groups in class. Yeah, it was just a review of exponential functions. So let's do this example. So I'm going to highlight a few things. So it says bacteria is growing in Mr. Edwards' refrigerator when he noticed there was 1.5 milligrams. So that's the initial amount. And then it says the amount of bacteria is tripling every 10 days. So this tripling part is very important, and this 10 days is very important as well. And then it says create a mass versus time graph. Okay, so basically I'm going to start by actually just putting one point in the graph. So we have an initial amount, and we can actually first start by writing our axis. So it says that they want a mass versus time. So time is going to be our x, and this time is in days. Okay, and then this is going to be our mass, and it's in milligrams. Okay. Okay, so now we have an initial amount with like 0 time or 0 days. So that's going to be our y-intercept of 1.5 milligrams. Just right here. Okay, and then now the way my group like approached this type of problem at the beginning was that we actually did a table of values. That way we can actually like plot it and then graph our graph. So that's what I'm going to also do here. And I'm going to call this x and y just for the simplicity. Okay, so x and y. So we already know that when x is 0, we got a y of 1.5. Okay, and then it's easy for us to just put in going up by 10, so we know that it's actually tripling. So 10, and then because our axis actually doesn't go past 9, it's kind of useless, but we can kind of still use that. So at 10, it triples, 1.5 triples. to 4.5. And then after 20 days, that 4.5 triples to 13.5. Okay, and we can't graph it unfortunately, but 10, it should be around here-ish. So we can see that shape. Okay, so now how do we actually come up with this equation for this graph? We can use the numbers that we were provided. So our base function for exponential functions was y equals b to the power of x. So this base number, what would that be? So here it says the amount of bacteria is tripling. So this tripling amount is actually going to be our base. And that's because it triples every time this exponent, like it's a whole number. So like for example, if this was 3 and 10 days later, like it multiplies by 3. So y equals 3, and then we have x, and then we still need to, it's not 3x, that doesn't make sense, we're given more information. So we have this initial amount that we can actually multiply at the beginning. Yeah. And this also gives us our y-intercept. And then our x value up here, or our exponent, is basically, the way I like to think about it is we're trying to divide it so that it accommodates each individual x value, so, or exponent value. So here it says it's every 10 days, but we want to divide that 10 days into each individual day, like time. So for example, if you had 5 days, it would be like 5 out of the 10 days, right? It wouldn't, like, we're trying to rationalize, I guess, like make it so that it accommodates the numbers that are above and below this number. And it, yeah, so for example, if we had 5 days, that would be half of the 10 days, and so you would only use half of that as the exponent. Yeah, so basically it would be what t is 10, so x divided by 10. Basically we're figuring out what the ratio is between the time that we're given and the amount that it triples by each time, which is 10 days. Okay, so this should be our equation, and we can actually check. So with our y-intercept, so for example, with our y-intercept, x is going to be 0, so 0 divided by 10 is 0. 3 to the power of 0 is just 1, because anything to the power of 0 is 1. 1 times 1.5 is 1.5, so that makes sense with our y-intercept. We can try 10. So 10 divided by 10 is 1. 3 to the power, we have to follow BEDMAS, by the way. So 3 to the power of 1 is 3. 3 times 1.5 is 4.5. And then if we try it with 20, 20 divided by 10 is 2. 3 to the power of 2 is 9. 9 times 1.5 is 13.5. So that's how we would come up with an equation. Basically, this base number is the amount that it's doubling, tripling, whatever, by halving, whatever. And then we have our initial amount that's being multiplied, and our time, our x variable divided by like the time frame. Okay, so now we can actually just plug in random values and get this shape. So if I plug in 5 into this equation, what will I get? So y equals 1.5, 3, and then we said 5 over 10, right? So it's going to be 3 to the power of 0.5 times 1.5, so it's going to be 2.6-ish. approximately 2.6 at 5, 2.6 milligrams. Okay, and then we can do like 9 because that's the closest to 10. I'm just going to plug it in here. So 3 to the power of 0.9 times 1.5. So it's going to be 4, which is really close to 4.5. Not that close, but like compared to the function, it is pretty close. So 4. And we can see that it's actually growing exponentially. But very slightly, but still growing. Okay, and so this would be our function. So now what we can do is actually go over the domain, the range, all the properties of the graph. Okay, so our domain, this is a review from grade 11. So x is an element of all real numbers, but in this case it is an exponential function, but in this scenario it is impossible to have negative time, so there is a restriction of x. It has to be greater than 0 or equal to 0. Our range, again, and there's no asymptote here because of the fact that there is a restriction, and yeah. So our range actually would be that y-intercept because the graph is always increasing. So YER, element of all real numbers such that y is greater than or equal to 1.5. Okay, so that's our domain and range done. We can do our y-intercept, which we already know. And in this case, there's no x-intercepts. So y-intercept is at 0, 1.5. Okay, and then we can do our increasing and decreasing intervals. This is the new thing we've been learning the last few days. So you can see that this graph is actually increasing, and it continues to increase forever. So, and it started off at 0, so we have that restriction, but it increases forever though. So from 0 to infinity, it's increasing. So x is an element of all numbers. What's that? 0 to infinity. And then because it's increasing forever, that means it's never decreasing. So the decreasing interval is never. Okay, and then positive and negative intervals. Gonna be similar answers to this. So yeah, basically positive would mean that like whenever the function is above the x-axis, and in this scenario, it never goes downward. It's always increasing. So this graph is actually positive from 0 to infinity as well. And same reason, because it's always positive, it's never negative. It is never in the negative intervals, so never. And then finally, we can do our end behavior. This is probably one of the hardest properties, at least for me. So basically, as x is going to infinity, our y value is increasing exponentially upward, so infinity. So as x is approaching infinity, f at x, so y, is approaching infinity as well. And then as x is approaching negative infinity, f at x, what is it doing? It doesn't exist, right? Because we have that restriction, so it does not exist. And those would be all our properties of this graph. Okay, and then finally it says create a graph of the same model, but time versus mass. So this is where we actually got stuck, but it's okay because we didn't learn this yet. So we're gonna flip these points and graph it, and it's gonna be fun. Okay. So time versus mass. Mass would be down here in milligrams, and our time would be here in days. Okay, so when our mass, when our time is 0, our mass was 1.5, which was our, now it is our x-intercept, and then we had a few points. So at 5 days, it was like 2.6. So at 5 days, it was like 2.6-ish. So up here, and then I think we got 9 and approximately 4. So at 9 days, it was approximately 4. So up here. And then if we connect these lines, we get a graph that looks like this. And this would be the inverse of the exponential function. And we learned a mini shortcut. So our equation was y equals 1.5, 3, and then x over 10. And we need to isolate for x, right? So what we can do, or up to where my group got, was 1, and then we divide by 1.5 to get rid of that. Because we're following BEDMAS, it would be x over 10, right? And then we got stuck here. And something new that we kind of learned, but still in the process of learning, is using logs. So if we take the log of 3 on both sides, that sets this side of the equation equal to the exponent. So log of 3 and then y over 1.5, this sets it equal to x over 10. And then now what we need to do is just get rid of this 10, and then we've isolated for x. Put a 10 up here. Okay. And that's how you would isolate for x. And it's okay if you don't completely understand this just yet, because we haven't really completely learned it yet. But it is the shortcut, or the way you would solve for the exponent. And this is the inverse equation for the inverse of an exponential function. And for practice, you should list all the properties. I'll post my solutions and you can see all the answers done on there.